everyone! Good day! My name is Eve Malibiran and my partner is Fatima Jane C. Inguito. And in this video, we are going to talk about our research proposal entitled The Use of Buck-Boost Converter in Maximizing the Efficiency of Grid-Connected Photovoltaic or PV System.
Chapter 1: The Problem and its Scope. Introduction. Solar energy has one of the highest potential to be used as the new source of electrical energy. The photovoltaic system today is facing lots of challenges that can affect the efficiency and the output power of the photovoltaic modules. The study of adding a buck-boost converter and MPPT controller to the standard components of the PV system is one way to solve this problem.
Statement of the problem. The promotion of solar energy utilization through photovoltaic system has become significant due to environmental concerns and the growing energy demand. The usual grid-connected photovoltaic PV system is confronted with many challenges to the reliability and the stability of the main grid. The buck-boost converter for grid-connected photovoltaic PV system is a proposed solution to make solar energy an economically viable competitor to oil and gas.
This study will address the following questions. Number 1. What is the maximum voltage that can be extracted from the solar panels using buck-boost converter? Number 2. What is the maximum power that can be delivered by this PV system with buck-boost? Number 3. Why is buck-boost converter the best DC-DC converter topology for the modified PV array?
Significance of the study. The result of this study will be beneficial to the following. First is the residential building. This study is a significant endeavor in maximizing the output energy of the PV system. Therefore, having a constant voltage supply from the buck-boost converter means having less fluctuations of energy supply. This makes every residential building that has PV system have enough electricity for their load and thus making their energy consumption from the primary source, which is powered by the conventional energy source, less costly. The excess power produced by the photovoltaic modules will be deposited to the grid, giving the consumer an opportunity to generate income. Residential buildings who do not have PV system can consider their decision to install solar panels because the benefits it can give to them. The next one is the institutional buildings. Institutional buildings like school buildings, hospital, and government buildings have higher consumption of energy. Having solar energy as their secondary source of electricity can lessen their expenses in electricity, especially with this study, where the PV system is using buck-boost converter and MPPT controller, thus harvesting the maximum power out of the PV modules. Since the PV system is on-grid, the excess electricity produced by the PV modules will be deposited to the grid, giving them the chance to generate income. The next one is the commercial buildings. Commercial buildings like malls, hotels, and supermarkets have higher consumption energy. Having solar energy as their secondary source of electricity can lessen their expenses in electricity, especially with this study, where the PV system is using buck-boost converter and MPPT controller, thus harvesting the maximum amount of power from the PV modules. The reduction of their expenses in electricity can make their profit higher. Since the PV system is on-grid, the excess power produced by the PV modules will be deposited to the grid, and giving them the chance to generate income. And the next one is the PV contractors. The improvement of the solar technologies is their improvement too. This study will make them be aware of the ways in improving the performance of the PV system. The improved PV system will attract more consumers, thus making their business more grown. The next one is the environment. Renewable energy technologies like solar energy are clean sources of energy. It has least negative impact of the environment compared to the other energy source. It does not produce greenhouse gases and does not pollute the water. Improving the efficacy of the PV system will make it have a better performance, thus making the people shift from using the conventional source of energy to the solar energy. Then the last one is the researchers. This study will be useful to the researchers who are also interested with the use of DC-DC converters on photovoltaic system. The information and the results in this study can be used as their reference. The recommendations of this study can also be considered in doing the research study.
Scope and limitation of the study. This study will only cover the use of buck-boost converter on photovoltaic system along with the use of perturb and observe method in determining the maximum power point of the photovoltaic system. The photovoltaic system is on grid. The result will show the output voltage, output current, and output power of the photovoltaic system with the use of buck-boost converter and without buck-boost converter connected between the photovoltaic array and the load. The cost of installation of this PV system depends on the contractor and the brands of components they will be using. Theoretical framework of the study. This study is based on the theory that DC-DC converters are an essential part of renewable-based electric generator systems. Photovoltaic generators and fuel cells generate unregulated electric power output, and they need to be connected to loads with strict voltage requirements. DC-DC converters serve as the power conditioner that can help the generator to provide a regulated power output. That is why in most facilities, DC-DC converters are a post-generator mandatory stage. In the case of our renewable power sources, which are subjected to constant fluctuation due to environmental changes, DC-DC converter enables the generator to work in maximum power. According to Miguel Godino, buck-boost converter is a DC-DC converter. It is a type of SMPS or switch mode power supply that uses the same concept of both a buck and a boost converter in one combined circuit. The main objective of a buck-boost converter is to receive an input DC voltage and output a different level of DC voltage, either step-up or step-down voltage, depending on what is required by the application. It can operate as a DC-DC step-down converter or DC-DC step-up converter depending upon the duty cycle. As shown in Figure 1, the input voltage source is connected to a solid-state device. The second switch used is a diode. The diode is connected in a reverse to the direction of the power flow from source to a capacitor and the load, and the two are connected in parallel. The control switch is turned on and off by using pulse width modulation.
Conceptual framework. In this research, the researchers have the efficiency of grid-connected photovoltaic system as the dependent variable, and the use of buck-boost converter in grid-connected PV system as the independent variable. The buck-boost converter is employed with the MPPT controller with perturb and observe algorithm for maximum power tracking. The MPPT controller is taking the voltage and the current from the PV module. Along with the perturb and observe method, they calculate a duty cycle for the buck-boost converter by introducing perturbation to the PV modules or to the array voltage. The MPPT controller sends gating signal to the buck-boost converter to increase or decrease the PV module voltage. To check whether the power is increased or decreased, then the duty cycle is adjusted accordingly to extract the maximum power of the PV module.
To further discuss the conceptual figure, the researchers show the flow of the electric supply from the primary source, which is the utility grid, and the secondary source, which is the photovoltaic system with buck-boost converter shown in Figure 3. The photovoltaic cells, which contain semiconductors, capture the solar radiation and convert it into electricity. The MPPT tracks the voltage and current from the solar module to determine when the maximum power occurs in order to extract the maximum power. The MPPT controller generates duty cycle in order to create switching signals for the buck-boost converter. The switching signal allows the buck-boost converter to operate the PV system at optimum voltage and current so that the maximum power extraction is possible. The buck-boost converter steps up or steps down the input voltage so that its overall output voltage is suitable for the voltage required by the electronic equipment. The DC output power is then converted into AC power to the DC-AC inverter. The AC power goes to the distribution panel where it is distributed to the load. When the electricity generated by the PV system is greater than what is being consumed in the load, the excess electricity is sent to the utility grid. When this occurs, the net meter spins backward, causing the electric bill to reduce. The net meter spins forward when the load pulled electricity from the utility grid, when the electricity from the PV system is not enough to power up the load.
Research methodology to determine the best DC-DC converter to be employed in a PV array A thorough step-by-step investigation is done as shown in Figure 4. First, we have to investigate the performance of the conventional PV array with the following conditions. All modules have sufficient irradiance, and one module is subjected to shadowing, thus having less irradiance. Then we have to modify the conventional PV array by implementing the following: the MPPT system and the DC-DC converter. Compare the performance of the conventional PV array and the performance of the modified PV array. Then we have to explore the perturb and observe or P&O algorithm used as the MPPT technique. Then investigate the following DC-DC topologies: buck, boost, and buck boost topology. Then determine the topology that best suits with PV systems in accordance with the chosen MPPT technique and the modified PV array. Then we have to evaluate the PV array system through circuit simulation in MATLAB Simulink. The researchers first evaluated the performance of the modified PV array, which has maximum power point tracking, algorithm, and DC-DC converter, and compared it with the conventional PV array. This is done by applying concepts and by using assumed values to get a general view of the operation of both PV array designs. Solar PV panels and inverters are used as a basis for ratings of the PV modules. For a typical residential and commercial installation, the PV modules are connected in series or parallel to form an array or a string. A conventional string-connected PV module in an array is shown in Figure 5. The array is connected to 90 to 520 volts and 11 amperes maximum input inverter. Each module has a maximum voltage output of 41 volts, a maximum current input of 10.98 amperes, and since the current is already very close to the maximum input current of the inverter, the modules are connected in series. The string is composed of 12 PV modules connected in series to achieve the maximum or very close to the maximum input voltage of the inverter. Considering that each module is working at its maximum, the string has a maximum current output of 10.98 amperes and a maximum voltage induced across the string by the inverter of 492 volts. The output power of the string is given by P string is equal to I string times V inverter, where P string is the power output of the string, I string is the current flowing through the string, and V inverter is the voltage induced in the string by the inverter. Thus, the output power of the string is 5402.16 watts. In this type of PV configuration, the efficiency of the entire array is reduced to the efficiency of the weakest module. This is because the connection is in series and the current is dictated by the weakest module. In Figure 6, it is assumed that the last module is subjected to less irradiance due to shading. Since the output current of the cell module varies directly proportional to irradiance, the output current of the shaded module decreased to 8.98 amperes. This module only has a maximum power of 368.18 watts, which is less efficient than the others exposed to the sufficient irradiance, which produces a maximum power of 450.18 watts each. When this occurs, the current of the system will now be reduced to 8.98 amperes and will result to the decrease of the power output of the whole string, which is 4,418.16 watts.
To address the energy loss due to the mismatch of its module in a string connection, a DC-DC converter coordinated with a maximum power point tracking algorithm is connected to its module as shown in Figure 7. The MPPT is always employed to always achieve the maximum power point of its module for it to operate at its maximum power. Mathematically, to extract the maximum power of the string-connected modules, the values of the string current and voltage of the PV modules at the maximum power point are determined. The string current is given by the current at the maximum power point is equal to the maximum power of the string divided by the voltage induced in the string by the inverter. The voltage of each PV module is given by the voltage of the module at the maximum power point is equal to the maximum power of the module divided by the value of the current at the maximum power point.
After getting the general view of the modified PV array design, a suitable MPPT technique is chosen. The perturb and observe or P&O method is used in this study for its simplicity. In this technique, the perturbation is introduced to cause the power variation of the PV module. The PV output power is repeatedly measured and compared with the previous power. The maximum point is achieved by repeatedly increasing or decreasing the output voltage. As the power increases upon the direction of the perturbation, the process is continued. Otherwise, the perturbation is reversed. Referring to Figure 8, if the operating point of the PV module is on the left of the MPP, the voltage is increased. However, if the operating point of the PV module is on the right side, the voltage is decreased. This is done by calculating the duty ratio and produce the control signal to the switch of the DC-DC converter. The duty ratio is decreased to increase the voltage and increased to decrease the voltage.
There are three basic DC-DC converter topologies: the back, boost, and the back boost converter. The back converter steps down the input voltage. The output voltage of this converter is always less than its input voltage. A conventional buck converter circuit is shown in Figure 10. The circuit operation depends on the conduction state of the MOSFET, the on state and the off state. In the on state, the MOSFET is supplying current to the load. Since inductor stores energy, the current through the inductor increases. This will cause the current in the load and the charge in the capacitor to build up gradually. During this state, the diode is reverse biased due to a large positive voltage on the diode. In the off state, the energy stored in the inductor is released back into the circuit. The back EMF from the inductor causes the current to flow around the circuit via the load and the diode. During this state, the diode is now forward biased. The load voltage begins to fall when the inductor has returned a large part of its stored current. To keep the current flowing through the load, the capacitor will act as the main source of current until the next on state.
Another DC-DC topology is the boost converter. The output voltage of this converter is higher than its input voltage. A conventional boost converter circuit is shown in Figure 11. The circuit operates in two modes. The first mode is when the switch is in the on state. During this mode, the inductor stores energy and its current increases. The diode is turned off, which restricts the forward current to the load. However, the load is supplied by the discharging capacitor. The second mode is when the switch is in the off state. During this period, there is a sudden drop in the current, causing the inductor to produce back EMF. There is now two voltages, the supply voltage and the back EMF. The diode in this state is forward biased, allowing the current to flow through it and charges up the capacitor and supplies the load. This steps up the output voltage as the inductor is now also acting as a source in conjunction with the input source.
The buck boost converter is a type of switch mode power supply that combines the principles of the buck converter and the boost converter in a single circuit. The output voltage of this converter is either lower or larger than the input voltage. A conventional buck boost converter circuit is shown in Figure 12. This converter will operate as buck or boost mode by switching the MOSFETs Q1 and Q2 on and off simultaneously. In buck mode, Q2 is controlled as always off and the output voltage is regulated by controlling Q1 as in a typical buck converter, while in boost mode, Q1 is controlled as always on and the output voltage is regulated by controlling Q2 as in a typical boost converter. In evaluating the results from the modified PV array, the voltages of the modules with sufficient irradiance were decreased, while the voltage of the module that was subjected to less irradiance was increased to achieve the maximum power point. As for the perturb and observe method, the maximum power point is achieved by increasing or decreasing the voltage depending on the operating point of the PV module on the PV curve. Therefore, buck boost converter is the best choice for the modified PV array system since it operates in both buck and boost mode.
Finally, when the MPPT technique and the DC-DC converter topology is determined, the modified PV array system was simulated using MATLAB and the results were evaluated. The block diagram of the modified PV array design in modular level is shown in Figure 13A. And the circuit diagram of the blocks are shown in the figures 13B, 13C, and 13D.
As for the calculation of the estimated cost of the project, the researchers used the following formulas. estimated cost per kilowatts is equal to cost of installation per watt times total kilowatts. Total cost of installation is equal to estimated cost per kilowatts plus mounting cost. Finally, the return of investment is given by the total cost of installation divided by the cost of energy produced.
The modification of conventional PV array design to further improve its efficiency has gained significant attention as the demand for solar energy as an alternative source is increasing. The use of buck-boost DC-DC converter employed with MPPT system will surely make a huge difference. And that is all for our research proposal. Thank you for watching.